Dear students, we are going to see about the asynchronous counter. First, we should know what is meant by a counter. A counter is a device which is used for counting the binary numbers. The counters can be designed by implementing the flip-flops in the circuit and also the combinational circuits for obtaining the special features in the counters. There are two types of counters. One is synchronous counter and another one is asynchronous counter. In synchronous counters, same clock pulse is given to the flip-flops at the same time. In asynchronous counter, different clock pulses are given to the flip-flops. How different clock pulses are given here? Initially, the clock pulse is applied to the first flip-flop. Then the output of the first flip-flop is given as clock pulse to the second flip-flop. Then the output of the second flip-flop is given as clock pulse to the third flip-flop and so on. Since the clock pulses are ripples in the circuit, we can also call this asynchronous counter as the ripple counter. There are so many types of asynchronous counters, but in our syllabus we are going to see about up counter, down counter and up down counter. Up counter means it counts the values in ascending order. Down counter means it counts the values in the descending order. Up down counter means it can count the values either in the forward direction or in the reverse direction. Now we are going to see the design of 4-bit asynchronous up counter using JK flip-flop. We can use any type of flip-flops, but here a JK flip-flop is used for designing a 4-bit ripple counter. So here I have represented a variable n which represents the number of bits in the counter. So it is a 4-bit ripple counter, so the value of n is equivalent to 4. So we need 4 JK flip-flops for designing the counter, and the counter can count the values from 0 to 2 power n minus 1 binary values. So 2 power n is 2 power 4 here. 2 power 4 minus 1 is nothing but 15. So the counter can count the binary values from 0 to 15. The circuit diagram and the timing diagram for the up counter is shown below. First we will see the circuit diagram. In the circuit diagram, 4 JK flip-flops are used. You know the structure of JK flip-flop. J and K represents the input of the flip-flops. Q and Q bar are the outputs of the flip-flops. So we are using the JK flip-flop in the toggle mode in the counter design. So the value of K and J should be equivalent to 1. And you can see the terminal of the clock. So in the clock pulse, in the clock terminal, we are going to give the clock pulse to the first flip-flop. So you can see one bubble at the clock terminal. So that bubble represents it is a negative edge triggering clock pulse. So negative edge triggering clock pulse means when the clock pulse transfers from high state to the lower state, that is from 1 to 0, that time only the flip-flop is activated. So you can see the output side of the flip-flop. From Q we are taking the output, and also Q naught is given as the clock pulse to the second flip-flop. Similarly, in the second flip-flop, from Q1 terminal, the output is taken and Q1 is given as clock pulse to the third flip-flop. Similarly, in the third flip-flop, from Q2 terminal, output is considered and Q2 is given as clock pulse to the fourth flip-flop. Similarly, from the fourth flip-flop and from the Q3 terminal, the output is taken. So we can consider this up counter is counting the values from 0 to 15, that is in the ascending order. So that only we are calling this as the up counter. And also in the circuit diagram, the first flip-flop represents the LSB bit of the binary value and the fourth flip-flop represents the MSB value of the binary value. So you can see the timing diagram here. The first clock pulse is applied to the first flip-flop. So when the clock pulse transfers its state from 1 to 0, that time Q naught is activated. That means we got the output at the Q naught terminal. So the Q naught is acting as clock pulse to the second flip-flop. So Q1 will consider Q naught as its clock pulse. So it will be activated during the transition of the Q naught from high state to the lower state. In the similar manner, Q2 will be considering Q1 as its clock pulse and Q3 will be considering Q2 as its clock pulse. So now we can see the truth table for up counter and also for the down counter. So the up counter counts the values from 0 to 15 and the down counter counts the values from 15 to 0. So which is in the reverse manner, that is in the descending order. So the up counter is nothing but the complement of our down counter. Now we are going to see about the design of asynchronous down counter. A 3-bit asynchronous down counter is shown here. So we connected 3 JK flip-flops in the circuit. If we want to design a 4-bit asynchronous down counter, one more JK flip-flop should be connected in the circuit. So here the JK flip-flop is implemented in the toggle mode. That is, the J value and K value should be equivalent to 1, and the clock is given as a positive edge triggering clock. The clock pulse is given to the first flip-flop. So positive edge triggering means when the clock pulse transfers its state from 0 to 1, then only the flip-flop will be activated. So coming to the output side, Q naught and Q naught bar are there. So we have to take the output from Q naught, and Q naught bar is used as the clock pulse for the second flip-flop. In the similar manner, in the second flip-flop, the output is taken from Q1 and Q1 bar is used as the clock pulse to the third flip-flop. So if I give the clock pulse from the Q bar terminal, then I can say it is nothing but the design of asynchronous down counter. So in asynchronous down counter, the binary values are counted in the reverse manner, that is in the descending order. So if it is a 4-bit asynchronous down counter means the values can be counted from 15 to 0. Up to this, we were seeing about the design of up counter and down counter separately. Now we are going to see how we can design one up-down ripple counter. So here we have to use one control mode input to select the up mode or down mode in my counter design. And also a combinational circuit is required between each pair of flip-flops connected in the circuit. So you can see the design here. I have to select which combinational circuit has to be designed in my circuit. So you consider a block diagram like this. So this block diagram consists of 3 inputs and 1 output. So M is a control input and Q bar are nothing but the output of the flip-flops. So Y is the output which has to be given as clock pulse to the second flip-flop, that is to the next flip-flop. So if my M value is equivalent to 0, I can say that is my up counting mode. If M value is equivalent to 1, we can say it is the down counting mode of the flip-flop. And I can say when M equal to 0, Q should be connected as clock pulse to the next flip-flop. If M equal to 1, Q bar should be connected as clock pulse to the next flip-flop. So now we are going to derive a truth table for this combinational circuit. You consider 3 inputs M, Q and Q bar. M is a control input. So I can have 2 power 3 equal to 8 binary combinations for my input quantities. So we can write the values from 000 to 111, which is nothing but 0 to 7. Now I am going to get the value of Y here. So what is my Y now? If my counter is acting as a up counter, then I should get Q as the output values for the clock pulse. So I should get the values for Y as 0011. So if my M value is equivalent to 1, Q bar should be the clock pulse to the next flip-flop. So the value of Y should be 0101, which is nothing but our Q bar value. Now we are going to draw a K-map for this truth table. So whenever I am drawing a K-map here, I can get the simplified Boolean expression for this combinational circuit. So we can get the simplified Boolean expression as Y equal to M bar into Q plus M into Q bar. Now we are going to draw a logic diagram by using the JK flip-flops for this up-down counter design. So here the circuit diagram shows the design of 3-bit asynchronous up-down counter. So since it is a 3-bit asynchronous up-down counter, 3 JK flip-flops are used here. Again the JK flip-flops are used in its toggle mode, that is J value and K value is equivalent to 1. And the clock pulse used here is a negative edge triggering clock pulse. We know that already. And also a combinational circuit is constructed between each pair of flip-flops, that is between first and second flip-flop. We have to construct a combinational circuit. This combinational circuit is going to decide whether the circuit is used as a up counter or down counter. If my m value is equivalent to 0, the circuit can be used as up counter. If m value is equivalent to 1, the circuit can be used as down counter. For example, you can consider m value as 1. So m bar is nothing but 0. So now you can see the circuit diagram here. The first AND gate is m bar into q. So m bar value is 0. 0 into qa. What will be the output here? 0 as the output of the first AND gate. And for the second AND gate, the output should be m into q bar. So m value is equivalent to 1 and qa bar 1 into qa bar is equivalent to qa bar. So these outputs of AND gates are given as inputs to the OR gate. Now we will get the output of OR gate as y. So y equal to 0 plus qa bar is equivalent to qa bar. So qa bar is given as clock pulse to the next flip-flop. So I can say whenever qa bar is given as clock pulse to the next flip-flop, that is nothing but the design of a down counter. If I want to design an up counter in the same counter, same circuit, we have to give the value of m as 0 and m bar as 1. So if m equivalent to 0, we will get the qa bar value as 0 and we will get qa in the output of the first AND gate, and output of y will be equivalent to qa. So qa is given as clock pulse to the next flip-flop. So I can say it is the design of up counter. So by using a single circuit, we can design both up and down counters. If I want to design a 4-bit asynchronous up-down counter, one extra JK flip-flop and another combinational circuit should be implemented in the circuit diagram. Next, we will see about the modulus counter. We can also call this as the mod counters. So they are defined based on the number of states that the counter will count through before returning back to its original value. For example, consider a 2-bit counter. A 2-bit counter can count the values from 0 to 3. So 0 to 3 means it has 4 binary values. So I can say it has a modulus value of 4. So we can call a 2-bit counter as mod 4 counter or modulo 4 counter. In the similar manner, we can design the mod n counters by using the JK flip-flops or any type of flip-flops. Therefore, a mod n counter will require n number of flip-flops which are connected together to count a single data bit, and 2 power n output states can be counted by using this mod n counter.